In this video, we're going to continue to look at general information on carboxylic acids and nitriles, focusing on spectroscopy. So what are the features we should be looking for? In IR, a carboxylic acid, you are going to see a carbonyl around 1700 inverse centimeters. You're going to see an acid OH, which is going to look very different than an alcohol OH. This is going to show up between about 2500 to 3500. And remember, this doesn't mean it's somewhere in between there. It's usually that broad and messy. And then you might also see a C single bond O somewhere between about 1000 to 1200. For nitriles, the most prominent feature will be the carbon-nitrogen triple bond around 2250. So if you recall, this is the same place where you see a carbon-carbon triple bond. So very similar in strength, which is why it takes similar energy to cause them to stretch. Next, for proton NMR with a carboxylic acid, the carboxylic acid proton, this is going to show up typically from about 10 to 14 ppm. So the highest ppm that we see in a proton NMR spectrum. These tend to be really broad, and sometimes it is really hard to see them, because if this is your baseline, then this might be your peak. So they tend to be very broad and very high ppm. Also keep in mind, if you have a carbon on the other side, then a hydrogen on a carbon connected to a carbonyl, this will show up around 2 to 3 ppm. For a nitrile, a hydrogen connected to a carbon that is connected to the nitrile, these show up around 2 to 2.5 ppm. And finally, by C13 NMR, carbonyls are going to be pretty high, like close to 200 ppm. More specifically, though, a carboxylic acid, this carbon is going to show up typically around 165 to 185. Definitely higher than sp3 hybridized carbons, and it's higher than alkene carbons, kind of on the high end of aromatic carbons as well. So if you have an aromatic and a carboxylic acid, it might be a little bit hard to distinguish the C13 signals. But you'll have other evidence, such as from IR, to let you know what to look for. And then finally, the nitrile carbon is going to show up between about 115 to 130. So again, this also overlaps with the alkene, now on the low end of the alkene or aromatic region, and so it could be a little bit hard to distinguish from other peaks depending on the particular compound. So now that we've discussed the numbers, let's take a look at a real example. This is our carbon-oxygen double bond right around 1700, and this is what we have. This whole thing here is our carboxylic acid OH. All right, so if you look closely, here we're at about 2500, right? So these are not just sp3 or sp2 CHs. In fact, although these are in the region just above and just below 3000, we can't really tell if these are sp2 CHs and these are sp3 CHs, or if this is just some of the shaggy beard of a carboxylic acid. Otherwise, in IR, this could be a carbon-oxygen single bond. Sometimes the carbon-oxygen single bond is also quite strong, usually not as strong as the double bond, but they're often significant and easy to find. This one, not so much. And then those are the features specific to a carboxylic acid. And then in this compound, we also have at 15 and 1600, this might be an aromatic. If we move on to the proton NMR, so here we have signal A. This is at almost 12 ppm. It's broad, not nearly as broad as the example I mentioned, but there's no splitting because the proton will exchange, so it doesn't see a neighbor, and this is definitely the carboxylic acid. Next, we have 5 hydrogens. It is a multiplet, so and this is at just over 7 ppm, so this is going to be a benzene with one substituent. Keep in mind, these hydrogens are equivalent to each other. They're different from these hydrogens, which are different from this one, but they're all overlapped on top of each other. And then we have, this was signal B, and now here we have 2 signals, C and D, and they're both around 3 ppm. So knowing what else we have present, one of these would be a CH2 that is next to a benzene, and one of them would be a CH2 that is next to a carbonyl. Whether this one is C or D, I'm not sure, and in this case, it doesn't really matter. The splitting is a little bit odd. It's kind of hard to tell what is going on here. So I think that part of the problem is that because these signals happen to have a very similar chemical shift, they start overlapping each other, which makes it hard to tell whether we're talking about a couple of doublets or some triplets or what's going on here. So there's definitely some information that's missing, but still we have enough information to put together a structure because we have benzene. Benzene is connected to a CH2 group, which could be connected to another CH2 group, which could be connected to the carboxylic acid. So this would be signal A, B, and then one of these is C and one of these is D. Next, if we look at C13 NMR, we have A, B. I think this is 2 peaks, so C and D, and then this one is E, and then F and G. So these are typical sp3 hybridized carbons. So these would be F and G. Don't know which is which and kind of don't care. This one would be A, the carboxylic acid, that's at 180, and then B, C, D, E, this is in the aromatic region, so that would be consistent with having one signal here, and then another signal, and another signal. So our compound here, this is called hydrocinamic acid, and this is the structure that corresponds to these spectra. Here we have another example, and we don't have a carbonyl. We do have some sp3CHs, and we have a signal here a little over 2200. So just looking at this, it's not clear whether this is an alkyne or a nitrile. And there's nothing else that really jumps out. This could look a little bit like an NH. It's a little bit too high though, because these are usually closer to 3300, so this is a little bit high, so I don't think that's anything that we need to interpret. So this might be it. Okay, so it doesn't look like we have any sp2 hybridization, no aromatics, anything like that. All that we can see here is either alkyne or nitrile. Next, if we look at proton NMR, so we have our signals at about 2.4, 1.7, and 1, and this corresponds to 2 hydrogens, and it's a triplet. So this must be a CH2 group. It's a triplet, so it must be next to another CH2 group, and it shows up at about 2.4 because it must be next to the nitrile. B is also 2 hydrogens, so this must be a CH2 group. It is a sextet, so it must have a bunch of neighbors. So it could have a couple of neighbors here and 3 neighbors here. and that would work. And then carbon C integrates to 3 hydrogens. It is a triplet, so this is a CH3 that has 2 hydrogen neighbors. So we have our nitrile connected to a CH2, CH2, CH3, and so this is signal A, B, and C. Now remember, from IR, we couldn't really tell if it was an alkyne or a nitrile. If this was a terminal alkyne, then number one, we would see a hydrogen on the alkyne in NMR, and we would see a hydrogen, an alkyne hydrogen here. If it was an internal alkyne, then we would have multiple signals around 2.5 ppm because we would have multiple groups on either side of the alkyne. The fact that we don't have alkyne hydrogen, and we don't have 2 signals for hydrogens on carbons next to an alkyne, that tells us that we can't have an alkyne and we must have a nitrile. So this overall, now that we're confirmed it's a nitrile, then putting it together like this makes the most sense. Finally, using C13 NMR, we have signal ABCD, and so our nitrile carbon is A, and then B and C are incredibly close to each other. So this is probably B and C, and then the CH3 group is a little bit lower, so that would be D. So this compound is butane nitrile. Make sure you keep practicing interpreting spectra and predicting what spectra would look like for a given compound.